Assalamualaikum. We are from Group 1. We'll be presenting about the electrical safety test on tonometry, which is more specific, the radial appellation tonometry. I am Sufiyatu Farzana. I will be presenting for the objective of this take-home exam. The objective of this take-home exam is to understand the working principle and application of radial appellation tonometry in the medical field. Second, to expose the students to electrical safety procedure and operation by using the safety analyzer like the Bentley Unimax and Regional Shift Test 60. Third, to measure different types of leakages that might occur to tonometry, like the earth leakage current and enclosure leakage current. Fourth, to allow students to make evaluation by referring to the standard of safety fixed by the IEC 6061. And the last one is to allow the student to design a simple testing circuit is able to test the current to detect the leakage of the tonometry. Now let us proceed for the introduction part. Radial appellation tonometry is a diagnostic device that used to measure the speed of pulses that travel within the radial artery system and changes leak rate. Radial artery is one of the branches from the brachial artery, and radial intra-arterial blood pressure BP is sometimes used as the reference standard for the validation of brachial cuff BP device. The radial artery is clinically significant as a medium to assess the heart rate. For the working principle of the radial appellation tonometry, it works by touching the sensor of the tool over the radial artery part at the wrist with mild pressure against the flat bone. The sensor that made up of strain gauge pressure will measure the wall deformation of the artery, and the pulse waveform will be recorded. Waveform analysis not only indicates central systolic and diastolic pressure, but also determines the influence of pulse wave reflection on the central pressure waveform. For the artery with high resistance or blockage, the pulse waveform will return faster as the diameter is smaller. Then, the waveform data will be analyzed through a special software derived with mathematical equation. Example of the patient that will be using this kind of device is the patient with PAD, which is peripheral arterial disease, which has the blockage at the passage of the blood due to the atherosclerosis, which is the accumulation of the fatty blood. In the medical field, knowing the arterial pressure is important to ensure the good circulation of blood in the body, which ensures all the organs to receive sufficient amounts of oxygen and indicates enough blood supply throughout the body. There is a parameter used to determine the normality of the arterial pressure, which is called as mean arterial pressure MEP. There are three ranges of the reading for the MEP, which is the high, normal, and low. The high range would be the reading above 100 mmHg, and the normal one is the 70 to 100, and the low one is below 70. For the high range, it indicates a person might be exposed to the disease like the kidney failure or the heart problem. For the low range, it indicates that the blood does not reach the major organ wells, which might indicate for the lack of nutrients of the cell that can lead to the organ damage. As the radial appellation tonometry is powered by the main, double insulated and CF line, it has to undergo electrical safety tests under the normal condition and single fault condition. Running under the normal condition is to ensure that the device can run properly and on a problem-free state. However, running under single fault condition is to ensure no hazard will be released even a single fault happen. So, this testing can be run using the safety test analyzer Bentley Unimax and Regional Shift Test 60.
Good morning, Doctor. I am Wapeling. So now I would like to present the theoretical calculation. These two figures show the human body model or network for IEC 60601-1. Here is the circuit show a person that equivalent to simulated human resistance and equals to measurement network. Here is the circuit show the Z input impedance. R1 equals to 10 kilo ohm, R2 is 1 kilo ohm, and C1 is 0.015 microfarad. All of this is plus minus 5% of error. This figure is equivalent to measuring device in IEC 60601 leakage circuit diagram. Based on the figure just now, R1 is 10 kilo ohm, R2 is 1 kilo ohm, and C1 is 0.015 microfarad. In Malaysia, the standard voltage is 240 volt, and the standard frequency is 50 Hz. Hence, we can calculate the impedance Z as below. We get Z total is equal to 995.52 ohm. For the self-designed measuring device, we only can find 10 mF capacitor in the medical electronic lab. So we use C1 and C2, there is 10 mF built in series, and C3 is 10 mF that is parallel with C1 and C2. So we can calculate that total capacitance is equal to 0.015 microfarad. That is exactly same with the IEC 60601 standard. So moving on to the next step, how do we calculate leakage current I by using self-designed measuring device? According to this IEC recommended LC measuring device, the voltage across the resistor for each test is measured and divided by total impedance set to get the leakage current value. Following the Ohm's law, V equals to IR. Rearrange the formula and to find current is I equals to V over R. So we can get of LC is equals to 50.7 microampere. Enclosure LC equals to 60.7 microampere. Patient LC is equal to 0.4 microampere, and patient auxiliary LC is equal to 0.1 microampere. All of this is a normal condition. Next, comparison percentage difference of leakage current values by using different devices. We calculated the percentage difference by using this formula, theoretical value minus actual value divided by theoretical value times 100%. Comparison between radio and measuring device. Of leakage current percentage difference is 34.85% and enclosure leakage current percentage difference is 882%. Comparison between bender and measuring device. For of leakage current percentage difference is 12.5%, and for the following enclosure LC, patient LC, and patient auxiliary LC, all of it is 99.9%.
Next, we can proceed to the test procedure. So for this safety test, our medical device is the tonometry, and we need to measure the earth leakage current, enclosure leakage current, patient leakage current, and patient auxiliary current for the normal condition and single fault condition. So we conduct the electrical safety test using bender, Rager 60, and our own measuring device. So for bender, we need to use under automatic test and the single test. For the automatic test, we have the without applied part and with applied part, and for the single test, we only find the patient auxiliary current. And for the Rager 60, we only measure the enclosure leakage current. So first, we use the bender to test earth leakage current and enclosure leakage current for the without applied part. First, the bender safety analyzer will connect to the tonometry, and then the 3-pin plug of the tonometry will connect to the bender, and there will be probes connected to the conductive part and the earth of the tonometry. Then we can start the test by following this flowchart. We can choose the following option on the monitor of the bender. So first the classification, then the IEC 60601, then because tonometry is the class 2, so we choose protection class 2, then without the PE connection, and type BF because the tonometry is the type BF medical device, then without applied part because we want to find the earth leakage current and the enclosure leakage current. Then we choose the complete test. Lastly, we can choose either automatic test, semi-automatic test, or manual test. For this one, we choose the automatic test. Next, for the bender with applied part, we can find the earth leakage current, enclosure leakage current, and the patient leakage current. For this one, it is the same, where the bender safety analyzer connect to the tonometry, then the 3-pin plug of the tonometry connect to the bender. Then we have the probe connect to the conductive part and the earth of the tonometry, and there's one more probe we connect to the applied part. Then, as before, the test can be conducted by choosing the following option on the monitor of the bender. So first, classification, then the same IEC 60601, protection class 2 without PE, type BF, and the lead, we choose the one lead because we only have this one applied part. Then we choose complete test, then automatic test. The next one is we use bender to test the patient auxiliary leakage current, where we use the single test. For this one, tonometry is connected to the bender safety analyzer, and the test probe connected to the conductive part, applied part, and the ground of tonometer, same as the previous one. Then the only difference is the option that we choose on the monitor of the bender. So in the main menu, we choose the single test, then we choose the next one, we choose the patient auxiliary current, where it will be tested under normal condition and the single fault condition. Next one, we use the Rager 60. Only earth leakage current and enclosure leakage current can be tested using the Rager 60. However, because of tonometer is the class 2 device, so there is no earth leakage current test conducted. So for the procedure, first, the main cable of the Rager 60 is plugged into the part 1 main inlet, and then Rager 60 will automatically power up in the home screen. Then a test lead is plugged into the part 2 black enclosure leakage probe to Rager 60, and the other end of the cable is connected to the ground of the tonometer. The power cord of the tonometer is also plugged into the tonometer to the socket in the Rager 60. Then, from the home screen, we can select this button to select the required language and standard 60601 because we want to test that one. Then we use this button to select from the home screen to perform the enclosure leakage current. This button is pressed on the home screen to test the enclosure current leakage. Then the test will automatically start when F2 key is selected and stop when pressing the other functional keys. So to test the current during normal condition and single fault condition, this is the sequence that we can follow. Then after we follow all these conditions, we can press this button to finish the test.
Hi, I'm Fahmi, and I will talk about the test procedures for own measuring device. The on measuring device is to test the four main leakage current, which is the patient leakage current, earth leakage current, enclosure, and also patient auxiliary leakage current. So what is the test procedures? First, a step-down transformer will be used to decrease the voltage to match the operating voltage of tonometry to 130 volts. And then make sure all the switches are off when we are not using it and on when we need to use it. The measuring device circuit was built using 1k ohm and 10k ohm resistors and combinations of different values of capacitors yield output of 0.015 microfarad. This is the figure shows the schematic and circuit diagram of our own measuring device. To test on the different leakage current, the probe will be attached to different places according to specific leakage currents. For this one is the earth leakage current setup. Both transformers live and neutral wires are linked to the tonometry live and neutral terminals respectively. Tonometry and the ground terminal of the transformer were both attached to the measuring device. For enclosure leakage current setup, this is same as before, except the difference is one probe connects to the conductive parts of the tonometry, which is the chassis. This one is the patient leakage current setup, which is the same before, but one probe connects to the applied part of the tonometry. The last one is the patient auxiliary leakage current setup. Live, ground, and the neutral terminals of transformer is connected to the live, ground, and neutral of the tonometry respectively. One probe connects to the applied part of the tonometry, and another one probe is also connected to the applied part of the tonometry. The voltage is measured and calculated using the Ohm's law V equals to IR to obtain the leakage current value. For results, this is the measured leakage currents with the applied parts using the bender, and this is with applied parts using the bender. For radial 60 measurement, this table shows the measured leakage currents using the radial 60, and this is the results of the measured leakage currents using the self-designed device.
Hi, I'm Unku, and now we will proceed to the discussion. For Bender Unimet Analyzer, no values for patient leakage current and patient auxiliary leakage current in Table 1 because applied parts are not connected during this test. Earth leakage current measurements are omitted in Table 1 and 2 although it is taken because tonometry has a Class 2 protection and Class 2 equipment does not have protective earth. Measurements taken are almost consistent across all test sequences and conditions, and all values do not exceed IEC 60601 limits. Moving on to Rigel Safe Test 60 Analyzer, no patient leakage current and patient auxiliary leakage current values at all because applied parts are not connected when using Rigel. Earth leakage current is also omitted because tonometry is a Class 2 device, and measurements taken do not exceed the standards across normal condition, open neutral fault under single fault condition, and reverse means condition. For self-measuring device, all four leakage currents are being measured except earth leakage current. Testing under any single fault condition is not conducted due to safety reason, as our self-measuring device is not fuse protected and we may have possibility of having electric shock. Leakage current values are obtained from calculation of voltage measured and by applying Ohm's law. As a result, this device is proven to be practical and functional, as all leakage current values are below the IEC 60601 limit. To compare all these values, percentage difference in enclosure leakage current between self-measuring device and Rigel is the largest, which is at 882%. Percentage difference of all other leakage currents are relatively high, which is almost double the original value at 99.9%. These high percentage differences may caused by self-measuring devices that have higher impedance due to voltmeter that is externally connected to the circuit, the number of capacitors used, and breadboard. Self-measuring device and bender also has lower sensitivity as it can only measure in milliampere, but Rigel can measure up to microampere. So our suggestion in improving our self-measuring device is by reducing the number of capacitors used by using a single capacitor that have a value of 0.015 microfarad. Also, we can use electronic screw terminal instead of breadboard for a more secure connection and less impedance, and we can also use less connecting wires.
What is the conclusion of this assignment? So this assignment main goal is to introduce us with the process of conducting electrical safety tests on medical equipment, which is in our case is tonometry, and we successfully extracted important information in medical device, which is the classification by identifying the logo at the back of the device. For this case, tonometry is a class 2 medical device and type CF protection class. Next, we also aware of how the Bender Unimed 1100ST and Regional Self-Test 60 operate, and we also now understand how the IEC 606011 acts as the standard for the safety limit and compliance of leakage current in medical electrical equipment. And only the medical device that successfully obeys this standard is presumed to be safe to use. And according to our results, tonometry is considered safe to be used either for patients and operators because all the leakage currents do not exceed the limits.